So if you prefer to stand out from behind the podium, you can tilt the monitor to face you, if that's what you'd like.
I'll be probably walking around a lot. If I walk outside, bring me back.
Well, you can do whatever you want. Yeah.
Thank you. Wow, that's a beautiful crowd.
Yeah. We don't usually do
Amazing. Very nice.
Your decision usually takes about 10 to 15 minutes.
Okay.
So they usually take
Okay.
45 to 50 minutes.
Okay.
If you want to spend more time talking.
No, I prefer having discussions over anything.
Yeah, no, I think you'll find it to be very good.
Okay, great.
Okay, everyone. Let's get started, please. So I'd like to welcome Professor Mary Flaska from Penn State University's Mechanical and Nuclear Engineering Department. I've actually known Dr. Flaska since I think.
Something like that.
When we were still working at Oak Ridge and then Michigan. And he's been at Penn State since 2015. Dr. Flaska's research interests, as you're going to hear a lot about today, are in radiation detection and then characterization and imaging. And the applications that he focuses on are often in nuclear nonproliferation, safeguards, and forensics. He's advised a lot of students throughout his career and has an incredible record of about 190 different papers in conference proceedings and peer-reviewed journals. Teaches quite a few undergraduate and graduate courses. So today, Dr. Flaska is going to tell you about some of the detection, characterization, and imaging work that his group is doing at Penn State University. It's all yours.
Thank you so much. Thank you so much for this way too kind introduction. And thank you so much for having me. It's a great pleasure to be here. This is my first time. Now, before I start, how many students are in the audience? How many students? Could you please raise your hand? Excellent. I'll be asking some questions so I know where to look. I've been at Penn State for 3 years, and it's great to see some former Penn Staters in the audience, and also some other people associated with Penn State. And before that, I was at the University of Michigan for almost 80 years as a research faculty, and before that, I was at Oak Ridge. And during all these stays, I've been working on radiation detection systems, and there are 2 projects I'd like to talk about today, and they are both associated with my most current research. But at the same time, if I start deviating from one of these 2 topics, apologizing ahead of time, I tend to do that. There are many projects I'm very interested in, and I would like to talk about all of them, but I was only given 45 minutes for today, so maybe I should visit again in the near future. But I have to tell you about Penn State, okay? I have to. It's a part of my contract. I have to introduce Penn State. We have 24 campuses in total. We have roughly 17,000 faculty and staff. And we're talking about, as of today, roughly 100,000 students. And the main campus, and this is the old main, it's the main administration building in the University Park. We have roughly 46,000 students on the main campus. We also have teaching hospital with roughly 1 million patients visiting per year. And we have over 500,000 active alumni. And this is why Penn Staters are so visible, because the number of active alumni is very, very impressive. And one of those 24 campuses is the World Campus, and Penn State is one of the pioneers in distant education. Now, the first project I'd like to talk about is one of my most recent projects, and this project was originally planned to be a 5-year project. Now it's a 3-year DITRA project, Department of Defense, and it's focused on detection and characterization of short-lived fission fragments. The idea here is that if there is a nuclear detonation, we have an emergency team that collects samples as soon as possible, ideally, and then the idea is to play nuclear detectives, as I call it, and try to find out who did it. Now, and there's a lot of data, a lot of unknowns associated with this problem, and one of the unknowns are short-lived fission fragments. And when I say short-lived fission fragments, I mean fragments with half-lives between seconds and maybe a couple of hours. That's what I call short-lived. This project started very recently, but I'm very excited about this project because we have done quite some work prior to this award. So I'll show you some results from my previous work. I've done with my collaborators. My co-PI is Amanda Johnson from Penn State University. She's a radiochemist. And then a former PhD student of mine from the University of Michigan, Bruce Pearson, who's now at PNNL, and he's one of the nuclear forensics analysts there. So the idea here is, and the reason why I have this slide here, because I know John loves these slides. So the main objective is really to use cyclic neutron activation analysis with tailored radiochemistry, as I call it, to analyze and measure, roughly speaking, 70 to 80 short-lived fission fragments, and to not just measure their half-lives, but also independent and cumulative fission yields. And then the second objective is to assess the feasibility of using these newly acquired data for a new non-destructive actinide mixture forensics assay. So really what we want to do here is to look at different samples, and I'll be talking about samples of interest. But before doing so, I want to introduce a little bit more my collaborators on this project. So this is Amanda. Again, she's right now, she actually just turned into assistant research professor. So that's her brand new title. And again, she's focusing on radiochemistry for nuclear forensics. She's an expert in nuclear activation analysis, which is obviously a very important component of this project. And then Bruce Pearson, whose work was actually focused on characterizing short-lived fission fragments, and I'll tell you some details about that. Now, here you can see our trigger reactor. This is a photograph from 1955. So those of you who have seen the area, the recent area, you can tell it's very, very different. I love that photograph. So why do we need, again, these short-lived fission product characterizations? Well, there are many applications, but again, this project specifically is driven by post-detonation nuclear forensics. And again, as I said previously, there are many unknowns, and we are trying to answer some of those unknowns. One of the reasons is to improve comprehensive nuclear testbed treaty mission objectives. So we are trying to improve detection limits, and we are trying to improve intelligence products. Now, previous work Bruce and I have done at the University of Michigan, and this work resulted in Bruce's PhD thesis. We did quite some work on the following targets: thorium-232, uranium-235, and uranium-238. And we published in 2017 in Nuclear Data Sheets fission product yields from these three isotopes of thorium and uranium using 14 MeV neutrons. Now, the reason why we use these high-energy neutrons is because the nuclear weapon has a fast spectrum. You don't expect to see many thermal neutrons. That's not the idea. Now, as you can tell, probably 14 MeV is nowhere close to the average nuclear weapon energy. But it's still better energy to be used than thermal neutrons. Now, what we are proposing for this project is to actually use fast neutrons from our trigger reactors at Penn State in conjunction with additional 14 MeV experiments. Now, when we look at the CTBTO, the International Monitoring System, there are 4 different approaches used. How the system processes data. It measures seismic activity, hydroacoustic sound, and atmospheric infrasound, and then we also detect radiation from the environment. And this is where we're trying to improve our knowledge by measuring a large number of fundamental nuclear data. So there has been a lot of work in this area over the last decades, but one of the most important achievements started at the Washington State University, where they used their trigger reactor and they measured neptunium-237, americium-241, and plutonium-239, and then the 2 uranium isotopes, 233 and 235, and they used pulsed irradiation, and they also used thermal neutron spectra. So it's not necessarily what we are trying to achieve. We need fast neutrons to better mimic a nuclear weapon spectrum expected. And then they measured what they called short-lived fission fragments between half-lives of 5 minutes to maybe a couple of days or a few days. Now we're trying to go down to maybe seconds to a couple of hours. Now anything short-lived they measured, they hand carried their samples to detectors, and anything intermediate with half-lives of days, they drove back the samples to PNNL, and as you would expect, all the data were acquired using high-purity germanium detectors. Now, before I continue, please feel free to ask questions at any time. Okay? If you don't ask me any questions, I will get nervous because I will think you don't care about what I'm talking about. So please ask. So, what are we trying to do? So we are trying to use our high-energy neutrons from our reactor. PNN also has a DT, a fusion neutron generator. It's 10 to 10 neutrons per second. I'm currently finalizing my lab with 2 DT neutron generators at Penn State. One of them is 10 to 10, and one of them is 10 to 8. The 10 to 8 neutrons per second generator has an alpha detector, so we actually have directional information about where neutrons, those 14 MeV neutrons, are flying. And I hope to have this lab available for this research by the end of this year. Please. Thank you. I appreciate it.
As I see here, so I see that you are getting this DT generator.
Yes.
So I assume that also it is a good magnetic field for the alpha particles to be directed.
We are looking into that. We are trying to make sure that we very accurately measure the emission of those alpha particles because the neutrons are flying at 180-degree angle. So obviously this alpha detector is very, very crucial, and this is one of the major delays why I don't have those generators yet, because the manufacturer has been struggling with acquiring high-quality alpha detector that would be able to manage 10 to 8 neutrons per second, or not neutrons, but alphas per second.
I'll come to visit you when it is ready.
Oh, I would love that.
Did you bring it here?
No. No. Good question, though. No. Now we're talking. Questions are coming. Very good, very good, very good. So our 1 MeV trigger reactor, and by the way, this is the oldest continuously working reactor in academia in the United States, okay? All right, that's another thing I have to say.
Yeah,
All right?
we replaced ours.
The flux is, as you would expect, up to 10 to 13 neutrons per square centimeter per second. Now our reactor core is mobile in 2 directions, and it rotates 180 degrees. And we also have 2 fast neutron irradiation locations, and this is very important for the project. And very recently we finished major upgrades of our trigger reactor, where we installed a new DO2 tank. And this is a drawing front view and back view. And now finally, after years, all these beam ports, and 5 in total, one of them is for cold neutrons, are focused on the core on the center of the reactor. This was not the case. At some point, the core at Penn State has changed, and the beam ports were not focused on the center of the core. And this has been changed because our trigger has gone through some modifications of the core. So the so-called fast neutron irradiator, this is a permanent reactor fixture, and again, these are the neutrons we are using for our project. There is 10-inch diameter aluminum tube and a lot of shielding, as you would expect. Now the fast neutron flux, and by fast, if I say neutrons above 1 MeV, we can get up to maybe 10 to 11 neutrons per square centimeter per second. If you go to lower energies, then of course you can go higher with the flux by roughly a factor of 2. Now, when you look at the spectrum, I have two references over here, Flat Top and Godiva. These are critical assemblies. And then I have Watt spectrum here in red, and then I have MCMP calculated fast neutron irradiator spectrum at Penn State. You can see that's a pretty nice spectrum. By the way, the new spectrum we are getting now is even harder than before because of this modification of the